This is a 2017 practice test free response portion. Question number 1, you've got a weak acid that is dissociating into the conjugate base and then some hydrogen ions. The dissociation is represented above. A student is given the task of determining the value of Ka for ethanoic or acetic acid using two different experimental procedures. The student is first asked to prepare 100 milliliters of 0.115 molar acetic acid using 2 molar standard solution. Okay, calculate the volume the student needs. So first of all, this is simply a dilution problem. M1V1 equals M2V2. The initial concentration is 2 molar. We're trying to figure out how much of that we need. So that's our V1 that we're trying to find. The final concentration is our M2. We want it to be 0.115 molar. And how much of it do we want? We want 100 milliliters. So to get V1 by itself, we're going to simply divide by 2. So we're going to take 0.115. We're going to multiply by 100, divide by 2, and I got an answer of 5.75 milliliters. And you did get 1 point for that response. Okay, so 1 point so far. Part number 2 says describe the procedure about how you would actually do that. So the way that they awarded points for that is, how do you get the 5.75 milliliters? That's really the first question, is how do I get that amount using these 6 things? Okay, and the best way to do that is, notice they have a 50 milliliter burette. Remember, that's what we use for like titrations and things like that. That contains the concentrated acid in it. So the first thing that you want to say is you want to say use the 50 milliliter burette to put 5.75 milliliters of the acid into a 100 milliliter volumetric flask. So you want to put that, you want to take that 5.75 milliliters and put it into the volumetric flask. Okay. And then basically you dilute it until you get to close to the 100 milliliter mark on the volumetric flask. And then you use the eyedropper to use drop by drop to get right where the bottom of that meniscus is, right on the line. Okay, so you got 1 point for saying use this, and then you got another point for saying get up to 100 milliliters using the volumetric flask. And then if you add that eyedropper part at the end, that's good as well. Okay, so that's a 2 point response, 1 for using this, 1 for using this. So we're up to 3 points so far. Okay, part B, using the pH probe, the student determines the pH is 2.92. Calculate the value of Ka. So first of all, the Ka expression is going to be the concentration of H plus times the concentration of the acetate ion over the concentration of the original acid. Obviously, we leave water out. And if we know the pH is 2.92, then we can take 10 to the negative 2.92 to find the hydrogen ion concentration. So 10 to the negative 2.92 is 0.0012. So we know the hydrogen ion concentration is 0.0012. And because it's a 1-to-1 ratio, we also know the acetate ion is also 0.0012. So the expression is 0.0012 squared over, and now the concentration of the acid is 0.115. So 0.115, remember it's going to go down by 0.0012, which again shouldn't make a difference. That's going to lower you a little bit. I would imagine you're still going to get the exact same answer. The Ka value is 1.3 with 2 significant figures times 10 to the minus 5th. If you didn't use this, I think you still get that exact same answer. Now, the way that they awarded points on this is they did give you 1 point for getting the correct 0.0012, and then another point for the 1.3 times 10 to the minus 5th. So part 1 was worth 2 points as well. So we're up to 5 points through part B. Okay, and then it says calculate the percent dissociation. So what percent of that 0.115 dissociated? So we started with 0.115. So that's what we started with. And then how much of it dissociated? Well, the concentration of the hydrogen ion is 0.0012. So we're just going to take 0.0012, divide by 0.115, multiply by 100, and I got an answer of 1.0%. Okay, and that is the correct response. You did get 1 point for that, so we're up to 6 points so far. Okay, in this other one, they do a titration, blah, blah, blah. They take a look at it. Part C says, write the balanced net ionic equation for the reaction that occurs when acetic acid and sodium hydroxide are combined. Now we've got a little bit more space, so I'll take up a little more space. So the regular equation should be the acid plus the base. Obviously, is an acid-base reaction. One of the things it always makes is water. H and OH making water. So our other product is going to be the sodium combining with the acetate. Okay, and that is not the net ionic equation. So now if things are soluble, we're going to split them apart. Okay, this is a weak acid that is not extensively ionized in water. So no, we are not going to split that apart. Sodium hydroxide has a sodium in it, so certainly we break that apart. Water never breaks apart extensively. And then again, something with the sodium, N, that's an N, sorry. And then the C2H3O2 minus. So the only thing that's the same on both sides are the sodium ions, so those cancel out. So my net ionic equation is the weak acid plus hydroxide making water and the acetate ion. If you leave the charges out, you don't get credit, so there's got to be that minus on the OH, the minus on the acetate, and that was just a 1 point response for part C. So I think we were up to, were we up to 6 points so far? Yeah, we were up to 6 points so far. So with part C, we are now up to 7 points. Part D says calculate the molar concentration of sodium hydroxide solution. Okay, so first of all, there's a lot of things we can take a look at here. In order to determine the concentration of the NaOH solution, we know the volume of the NaOH that was added to reach the equivalence point was roughly, looks like right around 14 milliliters. Okay, but now we need to know how many moles of base did we need. Okay, well, to figure that out, we have to figure out the moles of the acid. So we have 10 milliliters of 2 molar acid. So we can use that to figure out how many moles of acid we used. So 10 milliliters is 0.010 liters times 2 molar equals 0.02 moles of the acid. And then therefore, to reach the equivalence point, you had to have 0.02 moles of the NaOH as well. Remember, at the equivalence point, those two are equal to each other. Okay, and now to find the concentration, we're going to take that volume, that 14 milliliters that we found, again, going to the equivalence point here, coming down here. We know that that equivalence point is very close to 14, if not right on 14. Again, based on what we know, 0.014 liters after converting our milliliters to liters. So 0.02 divided by 0.014 gives me a final concentration of 1.43 molar. Okay, and they gave you 1 point for having the correct moles of the acid. So 1 point there, and obviously you got another point for having the correct response. So that's 2 points, so we're up to 9 points so far. Okay, and then the last one, explain. It doesn't say do it, it says explain how the student can estimate the value of Ka for the acid using the titration curve. So just using the titration curve, we know that at the half equivalence point, the pH equals the pKa. So I would go back to a pH or the volume of 7, go up, go over, and that is the pH. So the pH, so in part E, use the half equivalence point, pH equals pKa take 10 to the negative pH, and that will equal the Ka value. Something along those lines, you would be fine, and that obviously is just a 1-point response, so that gets us to our 10 points. Okay, so give yourself a score out of 10, and let's go on to question number 2. Oh, all the way to 3. That was quick. Question number 2. A student investigates the reaction between hydrogen peroxide and NaOCl, which is represented by the net ionic equation shown above. Is the reaction represented above a redox reaction? How do you know? You look at oxidation numbers. In any peroxide situation, the oxygen has an oxidation number of -1. Over here on the product side, when it's with water, it's -2, and when it's in its elemental form, it is 0. So the oxygen here goes from a -1 to a -2. It also goes from a -1 to a 0. Okay, remember this is called a disproportionation reaction, where the same substance is being both oxidized and reduced. So is the reaction represented above a redox reaction? Absolutely yes. Yes. Okay, because oxygen is both oxidized and reduced. Okay, and that's all you have to say on that one. I'm sure that's just a 1-point response there. Verify that. Yes, that is just a 1-point response there for part A. Part B gives you the value of delta G, gives you the value of delta S, and then asks you for delta H. So we know, first of all, that delta G equals delta H minus T delta S. So to find delta H, we're going to take delta G plus T delta S, and that will give us our delta H value. So the delta G obviously is -197 plus the temperature. Again, there's our temperature, 298. And again, careful with your values here in terms of units. You've got kilojoules here, you've got joules here. You have to make them the same. So with entropy, you pretty much always convert that to kilojoules. So move that decimal point 3 spaces over, and that becomes 0.144 kilojoules per Kelvin mole. And then we multiply those two together, add it to -197, and I got a final answer of delta G equal to -154 kilojoules per mole. Units not necessary. And that also was a 1-point response. So we're up to 2 points now through B. Letter C, does the temperature increase, decrease, or remain the same as the reaction proceeds? Well, we just calculated delta H. Based on your answer to part B, you answer part C. If you got a positive value, then you better say the temperature decreases. Okay. However, if you got the right answer and you got a negative delta H here, which you should have, then that's releasing heat. When it releases heat, what happens? The temperature goes up. Okay. So you would say it is going to increase. And why is it going to increase? Because it is an exothermic process. Okay, and that also, again, so far we're just 1 point for each of these. Letter D is the same way. Calculate the value of the equilibrium constant for the reaction at 298. So we know that delta G equals -RT times the natural log of K. So to find K is going to equal E to the negative delta G over RT. Okay, and remember that the R value that we use here, it is still the gas constant. But remember, anytime we're dealing with kilojoules, we don't use 0.08206. We use the 8.314. Okay, but remember that 8.314 is in joules per mole Kelvin. So we do want that in kilojoules. So the delta G value, so we're going to go E to the negative. The delta G is a negative. Be careful of that double negative there. So -197 over the R value, 0.008314, times the temperature, so times our 298. Okay, So put that into your calculator. Again, that double negative there, you can just cancel them out. So just make it positive. So just go 197 divided by 0.008314 divided by 298. And then take that lowercase e. It should be right above your natural log button. Take e to that number. And you should get a final answer of 3.36 times 10 to the 34th as your final answer. And that was also a 1 point response. So you're up to 4 points there through part D. Okay, part E says calculate, again, they give you some more information. Calculate the volume of 0.8 molar hydrogen peroxide that the students should use to add to excess NaOCl to produce volume, pressure, temperature. Volume, pressure, temperature, PVNRT. Volume, temperature, pressure. You always know R. What's missing? Oh, moles. So we can use those values to find the moles of oxygen. So N is going to equal PV over RT. The pressure is 0.988. The volume is 0.040 liters, moving that decimal point 3 spaces to the left to get to liters. R is 0.08206. And the temperature is, of course, 298. We divide, we multiply, we divide, and I got 0.00162 moles of O2. Okay, and you did get 1 point for that answer. That is not your final answer, but if you got that far, you got a point. Okay, and then using the balanced equation, we know that 1 mole of O2, so going back up to the very top, 1 mole of O2 is 1 mole of H2O2. So obviously you get the same number of moles of H2O2. And then that is the moles. So you know the concentration of H2O2. We now know the moles of H2O2. And now they want to know the volume. So think about molarity. Molarity equals moles over liters. We know this and we know this. We're trying to find this. So again, when you do that, you flip these two, the liters and the molarity, just switch. So the volume, liters equals moles over molarity. So the moles are 0.00162. The molarity is the 0.800. Okay, and when I divide those two, and again, you can leave this in liters or put it into milliliters. It doesn't really matter. If you leave it in liters, it'd be 0.00202 liters. Or, obviously, if you put it into milliliters, 2.02 milliliters. Okay, and obviously you got 1 more point for that, so that is a 2-point response. All total, I believe we were up to 4 at that point. So yes, now we are up to 6 points through part E. Okay, part F, based on the diagram, what volume of gas was produced? So remember, you have to go 1 digit past what you're certain of. I'm certain that this is 35, this is 36, this is 37. I'm certain that the number is somewhere between 36 and 37. I don't know exactly where, so I'm going to go 1 digit beyond what I'm certain of. So either I'm going to make it, and anytime you do this, make it either 36 right on 36 or make it right in between 36 and 37. So, and if you put 36.3 or 36.2 or even 36.1, that's fine. I would always go just right into the middle between them, 36.5. But again, if you put one number past that 36, whether even it's 36.0, they might give that answer to you if you put 36.0. If you put 35, no. You always have to read from the bottom of the meniscus. And again, we're uncertain about this number right here, so that number doesn't have to be exactly 0.5. But just know that, again, on the AP test, they're expecting you to give one number beyond what you're certain of. And really, and that's how you do science, is you always go one number where you're estimating. Okay, part 2, assuming that all the gas in the tube is oxygen, calculate the percent yield. Well, we were supposed to get 40 milliliters. We only got, again, whatever number you got there, 36.5. And obviously, part 1 here is only worth 1 point. So that actually gets us up to 7 points for part 1. Okay, so percent yield is just what did we actually get and what should we have gotten. 40.0 times 100 to get a percent, and I got a percentage of 91.3%. That is just a 1 point response, up to 8 points so far. Is the assumption that all the gas in the tube is oxygen? Is that correct? Well, you're collecting a gas over water. And anytime you collect a gas over water, here's all this water here, you've got all this water in here in this tube. Anytime you do that, some of this water is going to evaporate and turn into a gas. That's why anytime you collect a gas over water, that total pressure is equal to the pressure of whatever that gas is, plus the pressure of the water vapor. Okay, so anytime you collect a gas over water, there's going to be some water vapor in there as well. Okay, so the correct answer is the assumption that all of the gas in the tube is oxygen. Correct? No, it is not. Explain. Okay, because water will also turn into a vapor, and some of that gas will be water vapor. Okay, so 1 point there. We're up to 9. Okay, and then part G. Considering your answer to part D above, do you agree or disagree with the fact that the student claims that the reaction reached equilibrium before the expected amount of O2? So first of all, using my answer to part D, what the heck was part D about even? Part D was the equilibrium constant. Equilibrium constant is to the 34th power. That is a huge equilibrium constant, which means that in general, what does that mean? It means that there's no reactant left at all. That even though we did calculate an equilibrium constant, there is no reactant left at all. And so we can't really say this is even an equilibrium system because that equilibrium constant is so large. Okay? So the student claims the reaction reached equilibrium before the expected amount of O2 was produced. Do you agree or disagree? I disagree. Okay? And again, all you have to say is the large equilibrium constant shows that the reaction has gone basically all the way to completion, or virtually to completion. Okay, and that was also a 10-point response. So that is our final question. Give yourself a score out of 10 on question number 2. Question number 3 talks about ozone. Tells you how to draw. There's a central oxygen bonded to 2 outer oxygens and are not bonded to one another. But then it does say at the very end, but draw the Lewis electron dot diagram and include all valid resonance structures, which means you can't just draw one. Okay, so ozone does have 18 valence electrons. So we're going to put one oxygen in the middle, put the other oxygens around it, complete the octet for the outer atoms. There's 16. I have 18, so I have 2 left over, so I've got to put those 2 on the central atom. There's my 18. The central atom doesn't have 8, so I'm going to take 2 from this right side and put a double bond there. Okay, and then I have to include all valid resonance structures, so if I put the double bond on the right-hand side, this time I'm going to put it on the other side. So basically draw it almost the exact same way. Put 6 dots on that one, only 4 dots on that one, and you actually did get 1 point for each of those. So that was a 2-point response that they gave you on part A. Okay, part B, what's the shape of the ozone molecule based on how you drew it? So this depends. If you drew it wrong, then this might change. But remember that it's based on bonds and lone pairs. So there's 2 bonds and 1 lone pair. So that should be a trigonal planar shape, but one of those bonds is removed, and so you are left with a bent molecule. Okay, a 1-point response there gets us up to 3 points. Okay, for the decomposition of ozone, this is the overall reaction that happens. That's the enthalpy change for the reaction. Again, moles per reaction means if 1 mole of this reaction happened, this is the amount of energy that would be released. So basically, if this reaction happened 6.02 times 10 to the 23rd times, that's how much heat would be released. Okay, they want to know what's the average bond enthalpy in an oxygen-oxygen bond in O3. Okay, so in O2, there's 1 double bond. Okay, and they tell you that is 498. Those are the bonds that are forming. In ozone, there are 2 bonds. Now remember, we draw these resonance structures where we have a double bond and a single bond. But remember that in real life, those bonds are equal to each other. There is no double and single bond, even though that's how we draw it. We know that it's the yellow and the blue. You put that together, it makes green. The real ozone molecule has 2 bonds that are equal in length and equal in strength. Okay? So when we're calculating the bond energy, we're going to take negative 285. So remember, the enthalpy change for the reaction is the energy of the bonds broken minus the energy of the bonds that are formed. Okay, so in this case, we know that we have 498 is the O2 one, and there's 3 of those. And then in O3, there's 2 of them, but in each ozone molecule, there's 2 bonds. So how many bonds are we breaking all totals? We're breaking 4 bonds all total. Don't use the number 2. You have to break every single bond. So we're breaking 1, 2 bonds, but then we're doing that twice because of those 2 O3s right here. So it's the energy of the bonds broken, so 4 times the energy of the bonds broken, minus, and now in O2, there's just that 1 double bond, obviously. In O2, but there's 3 of them. So then we're going to go minus 3 times, and then we're going to do our 498. Okay, and now we just solve for x. So I'm going to add this part right here. I'm going to add that to the other side, and then I'm going to divide by 4. When I do that, I get an x value equal to 302 kilojoules per mole. Now, they did give you 1 point for the correct setup. So if you use the number 4, if you have the 3 times 498, if you have the setup correct, they gave you 1 point for that. And then they also gave you a point for the correct answer. So we are up to 5 points there so far. Okay, now we can see that concentration changing over time. And then in part D, based on the graph on the previous page, determine the half-life of the reaction. So excuse me. If we start with 1 times 10 to the minus 5th, how long does it take for half of that to go away? Well, from 1 down to 0.5, which would be right here, it looks like it takes 0.01 seconds. Then to go from 5 to 2.5, it takes another 0.01 seconds. And then from 2.5 to 0.125, so clearly we can see there is a consistent half-life here. It's a constant half-life here of 0.01 seconds. So we know it's first order. We also know it's first order because they give us the rate law here, and that rate law does have O3 to the first power, so we also know that's another reason it's first order. So determine the half-life of the reaction. It is 0.01 seconds. Okay, and that is a 1 point response there. So let's see how many points we were up to 5 points, so now we are up to 6 points through D part 1. Okay, D part 2 says calculate the rate law, okay, and include units with your answer. So if we know the half-life is 0.01 seconds, and we know that it is a first order reaction, we know that half-life is equal to 0.693 over K. So if they're asking us for K, then we're just going to take K equals 0.693 over the half-life. And the half-life again is 0.01 seconds, so 0.693 over 0.01 seconds equals 69.3, and that is seconds to the minus 1. And again, when they say include units with your answer, it means we're going to give you points for your units. So they did. You got 1 point for having the correct answer, and then 1 point actually for having just the correct units as well. So 2 points there. So we're up to A. 8 points. Okay, part 3 says, considering the relative concentration of the reactant. So what that means is go back up to the very beginning and notice that the concentration of the HSO3 is about 60 times greater than the concentration of the O3. So they're saying, consider the relative concentration of the reaction. Briefly explain why the data in the graph are also consistent with the following rate law. So they're saying, well, if it worked before with only the O3, now it also works with the HSO3 as well, being first order. Okay, and I wanted to show you what this is the scoring guidelines that they use. So right here, part 3, it says the data are consistent with that rate law because the concentration of HSO3 minus remains essentially constant during the experiment. So because it's so much greater than the value of O3, as O3 changes, the HSO3 is not going to change significantly at all. So basically, it's like you're adding a constant into that rate law. And again, I've never seen a question like this before, so it's kind of an oddball question. But anytime if you can add this HSO3 here and it doesn't affect the overall, it doesn't change very much, then they say, yeah, you can go ahead and throw that into the rate law. So you can see they did give you 1 point for that answer as well. And then the last one, also a 1 point answer, it says, what could you do to test that basically? Is you could remember when we did trial 1, trial 2, trial 3, trial 4, and then we determined the rate law from that. Basically, that's what you're saying you can do. They say do the experiment again and change those concentrations of HSO3 minus. Okay, and so that was also a 1 point response as well. So you got 1 point here, 1 point here, so that's 9, that's 10. So those are the first 3. So give yourself a score out of 10 there, then give yourself a score out of 30, all total for those first 3 questions.